What we are planning to do today is to go through Turan-Kubilius. Hopefully we can do all Turan-Kubilius. Then tomorrow morning we'll see maybe some application. And in the afternoon we'll see something about the distribution function for arithmetic functions and start the additive part. Okay? So I have shifted my notes, and so it can be a real mess. There is some chances that it is a mess. So possibly the numbering is still okay. 2, 2 is Turan-Kubilius. Inequality. So I have to tell you what are the actors. So okay, we consider let f be an additive, a complex additive function. So we have f of n, which is the sum. I don't want to write too many things. F of n, let us say, is the sum over p nu divides exactly n. We said already what it is of f of p nu, and we have the convention that f of 1 is 0, which is the empty set. You sum over the empty set, so an empty sum is equal to 0. So when n is given, and essentially there will be no limit here. This is why we can speak about limit of measures only after Turan-Kubilius. We do everything when n is finite. So we look at the measure associated to the n first value of f, which is the following, which is 1 over n summation 1 between n between 1 of capital N of Dirac function of f of n. Well, first there is here something which is fine, but it may be convenient when we go the other way around to say what is the weight we put at the point f of n, and if f of n is obtained several times, it may be slightly difficult. So in some way we may assume, we write it in little thing, that we assume that f of n plus 1 different from f of n2 if n1 different from n2, and let us say, and fn1 and fn2 different from 0. If they're equal to 0, they can be equal. You don't care much about that because in any case you are putting nothing in the sum. One way to do it is you just slightly shift your function, and you see that at the very end what you get will be okay. So in some way when we say that we are weight at a certain point, this point is well defined. Okay? This is some harmless condition. You just modify it a tiny, very tiny bit so that it's true, and at the very end shift it again and it will be okay. Okay, so what we have is the following, that the expectation of f among the first value is what we denote by 1n of summation n, always between 1 and n, of f of n. So this is the expectation, and this is the expectation associated to this measure, if you wish. Okay, so now this is in some way a good candidate for representing f. We are thinking of something like normal order, you see? So normal order, think of the function little omega or capital omega. The mean value is something like log n, and this is the order. So it's fine. What we wish, and this is the problem, is to say something about the variance, okay, which may be difficult in the real life to estimate. Okay? So what we need now is we wish to get an upper bound for what is in the real life Vn of f, which is the expectation with respect to n of f of n minus expectation n of f squared. You have the idea of what it is when you have values depending on f, what is the expectation. It is just the mean value of the first term. So this will be the mean value of the first term. You get that. Okay. So now we have to understand how it goes. So I try to write here something which is, how to say, I don't know, correct or definition. And what is imagination, I will put there. Okay, so in some way you can follow what is here, but in some condition you may say, why is this guy doing these things? So I try to explain you there why I'm trying to do that. So okay, what is the heuristic probability whatever it means, the frequency, prefer, that an integer in 1n, we're always living in this interval, is divisible, is exactly divisible by p to the nu. Exactly divisible by p to the nu, I mean by that p to the nu is that n is divisible by p to the nu, but not by p to the nu plus 1. Okay? So, well, this is not too complicated. You do the following. You consider what is the operator for the mean value, the measure for the mean value of the first integer is this measure, delta n. And so what we are looking at, we are considering the set A, P nu, which is the set of n such that P to the nu divides exactly n. Okay? Sorry?
Small n less than capital N?
Delta small n is the direct measure at the point n.
N is not less than or equal to 1, less than or equal to n. In the sum you have to put this up.
Ah, yes. Sure, thank you. Yeah. N is between 1 and capital N. Yes.
In the variance, it's E n of n small n?
Yes, this is the expectation of f. Maybe you can write it f if you wish. Okay. This is a function. When you take it at the value n, you have that.
But when you write x, you mean the value actually, right?
Sorry.
As you said yesterday, when you said x, you forget that it is actually the value of x, like x of u, collection of all n such that x of n belongs to a.
He's saying that you made a point yesterday that the function and its value you are differentiating. So f of n is what is objective to.
Okay. So, well, I'm not sure I understand, but I mean, okay. Well, when you said the function 2x, you understand what it means, and it means the function with 2x associated 2x, and you write it, I don't know, mult of 2, or because it is the multiplication by 2, or means very often you write a function as the value of the function, but this is not your objection. No. What is your point?
I am selling a good orange. Then you said that orange, of course, it's orange. So we erase oranges.
Oranges.
You say the example. You said, I mean, you told the example that
Yes.
the guy is selling oranges.
Yes. And we are suppressing. But in some way, this is the same way to describe a function f, to say f of n, that to say f. But okay, you can simplify, but good. You are right. Okay, so this is a p nu. This is well understood. It is all the integers which are divisible by nu, and I want to know how many there are among the first terms. So what I am interested in is what is nu n of this set, AP nu. This is exactly the number of n up to capital N which are divisible by p to the nu. Okay? Good. And this I can compute it also. This is 1 over n times n divided by p to the nu minus, of course, here I am taking too many elements because I am taking also the elements which are divisible by p to the nu plus 1. So this is minus n to the p to the nu plus 1. And as we know, this is not big computation. This is 1 minus 1 over p divided by p to the nu plus a big O of 1 over n. Okay? This is 1 minus 1 over p. I don't know if you read it correctly, but... Okay, so this is fine. So now what we do is we see that in some way we have something which is a geometric, a random variable which follows p being fixed, which follows what we call power, or how is it called, geometric law, okay, because you have p to the nu. Good. So this is interesting, and so we know that if you have, if yp follows a geometric law with the right parameter 1 minus 1 over p, then the probability that yp is equal to nu is close to that. Good. So now what we do is the following. You forget about that. I mean, you don't forget, but we are going to build our probabilistic model. And to build our probabilistic model...
The parameter is 1 minus 1 by p.
Sorry?
The parameter is 1 minus 1 by p.
Yes, I don't know if the parameter is p or is 1 minus 1 over p or 1 over p, but it's something like that. Possibly the parameter should be 1 over p.
1 over p.
Yeah. And this is...
What's the geometric law?
Something that is exactly like that. That is to say, the probability that something is equal to nu is proportional to something to power nu. And when you want to sum it, you are just summing a geometric series. Okay? And you find this number so that this is the sum, the total mass is equal to 1. Okay? So what is important, the parameter should be 1 over p, and then you just adjust so that the total sum is equal to 1, and you know how to sum a series. So now we do the following. We introduce, now I am working in the model, probability space, large probability space, I don't care much, omega p, and random variables. Leave some space before random variables. As I do, I will add something later on. Random variables, zeta p. Of course, this depends on f also. If you want to say, this depends on p and on f, such that they follow a geometric law. That is to say that the probability that zeta p is equal to f of p nu, and this is why you see I need to have different values if they take the same value, and maybe in a difficult situation, that this probability is equal to 1 minus 1 over p times 1 over p to the nu. Okay, and this is for nu is from 0, 1, 2, and so on. Good. So in some way this is fine because it looks like the probability that an integer is something which is divisible by p to the nu, or that the value of the function is exactly f of p to the nu for this random variable, and then we are going to make the sum because we want to get something like that. Good. So this is fine, and we let z of nf to be the sum of p up to n of this zeta p. Okay. You may assume that f of p to the nu is equal to 0 if p to the nu is larger than n. There is not much difficulty about that. Good. So this is our model, and if we compute, so we may assume, and we assume that what the probability of no, this I cannot do, but what I can assume is that f of p nu, I can assume it here, that n given, I assume I made some modified f with respect to n, but I am not using this any longer, that f to p nu is equal to 0 if p nu is larger than n.
So it's actually the parameter is 1 minus 1 by p. Because you were saying that after many terms, nu plus 1 position is the success, other are failure.
Sorry?
So you're saying that first p many are the failures and the p plus nu, sorry, first nu many are failures and nu plus 1 many, one term is the success. So that parameter is 1 minus 1 by p.
Okay, good. You call the parameter as you wish. I have no idea about that. This is a definition of a random variable. Now you call the parameter whatever you wish. In any case, you can go from one to the other. This is not a problem. Okay, so this will be my zeta of n and f, this function. And I know what is the expectation. The expectation on z of fn and f is something which will be the sum when p to the nu is at most n of f of p to the nu divided by p to the nu times 1 minus 1 over p. Okay, you call the parameter wherever you wish. Now, this is fine. So you see, if I have a sum of random variable, getting the expectation is easy. Now, you know that all our business will be to go to the variance. So if we want to go to the variance, it's whether they are independent or not. But we cannot just say like that they are independent or not. We have to say, does it make sense in the model? Okay? So again, I am going to say something which has nothing to do with the, I can define abstractly the model, but I want to understand why it makes sense. Okay? So this is this part which, it reminds me of discussing with Chevalet after a course that Chevalet was giving. It was always, you see, a very abstract geometry, and I was asking a question to Chevalet, so Chevalet started to make some little drawing like that, and erasing it and giving a completely formal proof of the assertion that I was asking for. So this, I shouldn't write it even, and just write that like that, and then you don't understand why you are doing that. Okay, but so I try to give you some imagination. Okay, so now I'm looking at the following, what it is if I take the intersection of p nu and q mu. Of course, I assume that p is different from q. Otherwise, they are strongly dependent. So, what is the measure of that? Well, we can compute what it is. It is exactly the number of elements which are divisible exactly by p to the nu and q to the mu. Okay? So you have the elements which are divisible by p to the nu q to the mu. This is fine. But then you count too many terms. So you see this some inclusion-exclusion formula, but only with 2 terms, so it's not too complicated. I will subtract those which have nothing to do here because they are divisible by p to the nu plus 1. I have also to subtract those which are divisible by q to the mu plus 1. But if I do all that, I have subtracted too many terms. So I have also to add the terms which are divisible by p to the nu plus 1, q to the nu plus 1. Okay, and this is an exact formula. Okay, now I can work a bit out what it is. And again, as usual, when you take the bracket out, you get something which is a big O of 1. So it tells you some big O of 1 over n, which is not that bad. And you have all the main terms, and you work a bit out what you get. And what you get is exactly 1 minus 1 over p, 1 minus 1 over q, divided by p nu q mu plus big O of 1. This is fine. And this is exactly the product of the 2 terms which are nu n of a p nu and nu n of a q mu. So this is nu n of a p mu nu times nu n of a q mu plus big O of 1 over n. So if n is in somewhere large enough, but n is always fixed, but if it is large enough, well, you say this is basically the same thing as the product, and so this is to say that your events are independent. So the fact to be divisible by p to the nu and the fact to be divisible by q to the nu, or the other way around for the exponent, no problem, are independent events. Good. Sorry?
The nu is not the original nu. This is a symbol.
What is the symbol?
We use nu two places. One is for the mean value, one is for this.
Yeah, nu is for the p and mu is for the q. And so what? They can be equal. I don't care.
Notation is objective to it's okay.
Why is this?
Because the measure is also different.
Because here is it should be mu. This is the point. Yeah.
Because your measure is also mu, so the mu and f, that mu is there also. So
This notation of
the third line in the
There is a mu somewhere.
mu and f they measure the weighted measure.
It's just the notation.
Oh, yes, but this nu has an index. It's completely different. There's nothing to do. This nu has no index. Okay. Good. So what you assume is that they are independent. Okay? If P is different from Q, then they should be independent. Fine. We have almost everything. Indeed, there is something which is a bit better than this one, or which is close to this one, but easier to work with. It's called the semi-empirical variance. You know, you have 2 ways to compute the variance usually. If you have a sample, either you work only with the sample. This is exactly what we are doing here. Or you have some idea of the law. You know, for example, what should be the mean. And if you know what should be the mean, you don't use the sample for getting the mean. You just the mean of the law. And then you compute the empirical variance, but with the expectation of the law. If you have done some statistics, you know what I mean. If you don't have done statistics, it's not a problem. There is something, and we'll see that it is not a big difference. So we introduce now something which is called the semi-empirical. It's not the same. Put a star. Now we're happy. Which is the following. It will be the expectation. So this is definition. Expectation and n of the function f minus something which will be En of Z and f, or E of Z and f, as you wish, square. So I take the expectation of the model and not the other expectation. So in some way we are going now to do something. We are going to compare in some way this with that of the original one, and compare this one with the one of the model. Instead of going directly, it will be easier technically.
So this is called what, sample value? What is it? What is this?
This is called semi-empirical. By the way, the p which is here has nothing to do with the prime number. If you like this type of thing, semi-empirical variance. Okay. So, I think now I have about everything to tell you what is Turan-Kubilius inequality at last. So, theorem Turan-Kubilius. Inequality. Got the following for any complex additive function. F, one has an NE and greater than 1, but of course it is of interest when n is large enough. So what we prove is the following. So this is the inequality which tells you that the semi-empirical variance Vn of f is at most something. This is not the best constant. There's a little things which is worse. I'll tell you what it is, times the variance in the model of Zn, Zfn. Znf, I put Nf, okay. Let us go on with Nf. So it tells you the following, that the variance, the real variance or the empirical semi-empirical variance, we'll see that this is very close to the variance in the sample, is at most 8 times this variance. Here we are just in a model, so it's much easier to compute what it is, and we'll compute what it is. This may be more complicated to get. Okay, and this is why we're happy to have something like that. Sorry? No, the other way. No, the other way around. Not really. It's not. Not exactly. Not exactly. No. It's usually close. We'll see a few inequality that goes in the other way around, but not with this one. You can build things which are a bit more stupid than that. So okay, now what is epsilon n? Because the interest in that is that epsilon n is something which tends to 0. I will write what it is. With something which tends to 0 when n tends to infinity, but which has nothing to do with f. Okay? So, where, let me write it, epsilon n is big O of square root of log n divided by log n. This is good, so it is a term which tends to 0 when n is large enough. And this term is completely independent, of f. So okay, now if you want to know what it is, I can write it for the sake of completion. You see it is a mess, but okay, epsilon n is the following. So in some way this is the end of the statement. Okay? And if you want to know what is epsilon n, it is 8 over n times the summation when p nu q mu is at most n with p different from q, and this is p nu q mu to the power 1/2 plus 4 over n times 2 times summation when p to the nu is at most n of p to the nu summation when p is at most n of 1 over p to power 1/2. Okay.
All n large, this will be large.
Sorry?
This is for any n or n large?
I mean, it's simply because you have log n. Okay, now you are happy.
But this constant is completely explicit, right?
Yeah, this constant is completely explicit.
So you mean if I perturb a little bit, nothing will change? This will remain as it is?
No, but then it can be rather large for small values, but for small values of n it is but essentially no, this is correct. You can put a constant. This is always true, but of course it is of interest when n is large enough. But even if you take n is equal to 10 or something like that, you are able to compute what is epsilon 10. Okay, it's not only asymptotic. The interest is asymptotic, but you can compute it for any n. Okay, or if you prefer to let n here, you put log of n plus 3, and then you are happy. And this is not the problem. So you can really, you know what it is. It's a mess, but you understand that here you have something. Essentially, what is important here will be to have something like p to the n is something like n, and then you have something, the sum of the p, which be something like log, and no, this is less than that because you have just prime numbers. So prime number is something like n over log n, and this is n over log n, and you have a log n, and when you get the square root, you get exactly that, and the other way you can work this out. Okay, but this is completely, it has nothing to do with f. Okay, and 8 also has nothing to do with f. And it's not a 4. I say that for you because in Bengali you would think that this is a 4. No, this is 8. I know you. Sorry?
In the sum of epsilon n.
What is? P and Q are primes. Always.
Phi, that is P. Inside the sum there is a phi, that is P. In the summation.
This is a P. This is the symbol. Yeah. This is what you mean? Okay. This is P. Okay. Fine. This is one thing. And also we can say what is about this in terms of the so in some way it has nothing to do with probability if you want to be I think I can answer your question. When do we start to do probability? You were asking this morning, and you are right. We'll do probability only when we do additive number theory. Then we really do probability. For the time being, we do nothing as probability. We build probabilistic model, but you can do everything without the probability, except that the probability will help you to understand what you are doing. You see, each time there were really probability, I was putting in here and immediately erasing. So this was one of the first remark, and the second remark is that we have VF, ZF, NF. I think I put the N first. Yeah. Okay. Contrary to what I put on my notes, but I have just to be consistent. This is at most 1 minus 1 over P times the summation when p nu is less than n of f of p nu square divided by p nu, and this is the same order of magnitude. It is larger than 1/2 times the same thing. So you see, in some way, you can suppress everything that has to do with probability if you prefer. This is why Delange was saying this is not really probabilistic number theory. It is the statistical study of arithmetic functions, essentially additive arithmetic functions. Good. Sorry? This depends on P, and this is not good that it depends on P, of course. This is not good that it depends on P, because this is the summation of P nu. Ah, yes. No, okay. Yeah, you're right. Simply let me put the 1 minus 1 over P inside the sum. This is the sum of all the P and all the nu which are less than that, and then you have this. Thank you. Yeah. Good. So now we want to, essentially we can stop here. I'll try to give a proof of that. So we have several things to do. One thing is to compute this variance in the model. Well, this shouldn't be too difficult. A bit messy computation, but not too difficult. And we would like also to say something about the difference between the semi-empirical variance and the real variance. Because having something here, we would like also to say that we are really not far of having something for Vn, the original one. Okay? And then to know how we can prove all that. Good. So, compute, it's here. So we start by computing V of Z and F, because we'll use that. Maybe this we don't need. Okay, so we write V of Z and F to be something which is Bn Bf of n square. Of course, everything depends on F here, minus F of a square of n, and Bf of n square is the summation when P is up to n of the expectation of zeta of P square. Okay, and this, you know how to compute that. It is the expectation. Something is not too complicated. This is just the summation, yes, summation when P nu is at most n. You know what are the values which are taken by this? This will be the f of P nu modulus square. And you know with which probability it is. You have always your geometrical law. So this is simply f of P nu square divided by P nu 1 minus 1 over P, which is the random variable which takes the value. If it is the modulus square, it takes the value f of P nu modulus square with the same probability as the other one was taking the value P nu. There's nothing new under the sun. So this is fine. And of course, the complementary part, Rf of n square, is given by the summation. We worked a bit on that this morning, for those who were not here this morning, that even if you have something complex, the variance of something complex at the sum of the expectation of the modulus square minus the square of the modulus in absolute value. So we worked a bit on that. And it is exactly as in the real case. There is really nothing serious about that. So it is the expectation of zeta p square. And this now is slightly more complicated, but not really. P up to n, of course, we are not interested in the other one, and then you will have something like that. Summation when nu is at most log n over log p. We're not interested in larger values of f of p nu divided by p nu square. You see, this is fine because we have this, well, okay, variable are independent, so the variance is the sum of the variance, and you get that. Good. Now the point is that this term is not much larger than this one. Rf is not much larger than this. It is at most 1/2 of the other one. Why is it so? Okay, what we can do for our Fn of f is do the following. This will be at most, why is it true this? Now it's already the case. You write it and then you try to understand why this is true. Okay, so I have to understand what is this. And so I have summation p up to n, this is fine, of, if I start like that, it's maybe a bit mad. No, okay. 1 minus 1 over p square. I should have worked directly on that, but it's okay. And so now I have the sum of the square, and for this sum, we are going to use Cauchy-Schwarz. Essentially, this is always, or Cauchy as you wish. If it is a sum, you call that Cauchy. So what is this? You take the fact that you have 1 over p nu, and you see you break this sum as being f of p nu divided by p nu is, you write that it is f of p nu divided by p to the nu over 2 multiplied by 1 over p nu over 2. Okay, which makes sense. And so now you are summing the two terms. So when you are summing the two terms, you will get something which is a summation of nu, within the same business, times this to the square. This is already to the square, so it's fine. You will have just 1 over p to the nu over 2 square, which is 1 of the p over nu. Okay, this is the first term. And the second term will be the summation of a nu, always up to log n divided by log p, if you wish. Here you don't care much because this converges very nicely. So you can break this and put a bit more terms. And then you will have something, by the way, this is real, so you don't care, but this is not real, so better to put it like that. F of p nu, no, I don't need that because I'm putting here something like that. F of p nu square divided by p nu. Okay? Now what do you get? You get the fact that this will cancel out, not exactly, but almost. What you'll get, this is 1 over p minus 1 times the summation when nu is less than log n over log p of this f of p nu square divided by p nu. Okay? And you want to compare it with this one. So it's nice because you have the p nu squared divided by p nu, and instead of having 1 minus 1 over p, you have something which is 1 divided by p minus 1. Does it make sense? No, it doesn't make sense because I was losing this sum over p of 1 minus 1 over p squared. Okay? And so now you are fine because you get something which will be essentially what is there if you use that. Okay, this is p minus 1 squared divided by p squared. Okay? So you have exactly the same thing. So you are happy. This is, no, wait a minute. We are winning something. Yes. Yeah, fortunately, there is a factor p in the denominator, and this factor p means that you are winning at least 2 for the first one. And so this is at most 1/2 of the BFN square. Okay? So this is fine. So in some way, for the time being, you know that VZN is something between this expression of Bn and larger than 1/2, because this is always between 0 and 1/2 of B of n square. Okay? So we have made the part which is to say, okay, you are expressing things in terms of the variance in the model. Let us compute the variance in the model. We know what it is. Good. Okay? So this is fine. Now, next step is to try to say something about the difference between the semi-empirical variance and the variance in the model, in the real variance, according to the sample.
So one can compute the actual value instead of the bound, right?
Sorry?
One can compute the actual value of variance of ZNF, right?
VZNF, yes, we know, yeah.
Because this is sum of those geometry random things.
Yeah, because you know up to a factor 2 what it is equal to. But you can also, if you don't want to have the factor 2, you can win a bit on that. This is why in some ways it's better to express the thing in terms of V than in terms of B. But
the actual value, you can easily express the variance, sum of the variance of that plus the covariance, because these are independent. So covariance will
yes.
be 0, and hence it will be the sum of the variance.
Yes.
So then, I mean, instead of finding just bound, you have the actual value.
Yeah, you can find it if you wish. Yes. Yeah, right. Okay. No, what I am saying is that even if I am losing, you see, a factor, this factor is not very important. So the 8 that I gave in the Turan-Kubilius is not the best possible. What we'll see in any case tomorrow, at least on one example, is that this bound cannot be reduced to 1. There are cases when the model is really better than the actual life. Okay, this is the something to keep in mind. Well, we put some 8. If you put something which is different, what is really important in the upper bound is that you have the 8, which is something completely absolute. You can put 2. You can put something better, and also the fact that epsilon n is something which has nothing to do with the function f. You can really compute it completely. Okay. Good. So essentially what we use it is to have some good bound for the variance, and once we have a good bound for the variance, we are able to say something that something is a normal order. You see, you use Chebyshev to do something like that. We can improve indeed on all this business, but okay. So now we want to know what is the difference between Vf of n and Vf star of n. Okay, to show that indeed if we get an upper bound for Vn star, we're happy. It gives you also a good bound for Vnf, at least asymptotically this time. So now what we are interested in is get upper bound for VNF star minus VNF. Okay, this is what we want to do. Okay, the first thing is that we have VNF star minus VNF square, absolute value, sorry, is equal to En of f minus EZNF square. How do we prove that? So you remember what were E of, what was this? This was F expectation of F minus what? En of F minus, this is the expectation, no, this is F minus, sorry, this is the expectation of the square of F minus En of Z and F square, and this is minus, and then we take the absolute value later on, and then it is minus the E of F minus En of F, En if you wish, En of F square. Okay? Why is it true, this relation which is here? It is always the same kind of business. What you do is you understand that you are going to expand this, multiply by the complex conjugate. So there are some terms which are going to disappear. For example, the F are going to disappear. Fine. The F are going to disappear, but they will stay in what I should call the double product. It's not really a double product because we are dealing with complex value, but it is the same thing as a double product, or the real part of the product of something like that. Okay? It will occur 2 times, but it is F times something which is a constant. And we are taking the average. So it's exactly like when we proved, we did that this morning, that the variance of x is an expectation of x squared minus expectation of x squared. Okay? So you have to make this difference, and what you are left with is only, since now you have either you have constant, which are those, or you are elements which are linear in F or in F bar, but then when you take the expectation, everything is just expressed in terms of the expectation, either the expectation of this or the expectation which is here. Okay, so I don't want to write it down, but I think there is nothing really complicated. Just make the product and understand that each time you have something which is basically, let us say, linear in F, with a coefficient which is some expectation, and so you will get the expectation, and you just have to check that what you get are exactly the terms which are here. Okay? So forget about that. This is done. This is a nice point. Okay? It's not the end of the business, but at least now we are on the expectation, and so we are on the safe side to get an upper bound, to say what it is. So let us try to see how it goes. And what are this thing? Okay, it should be here. Okay, so let us start by trying to see. So we have the following. So okay, we agree on this. We understand how we can get it, and I don't want to do it. Now I say, what is En of f minus E of z and f? Do that. This is at most, and possibly you have to understand what it is. It's maybe not that. This is not completely obvious. Maybe I have to write down what it is. I should have kept everything on all the boards, which is not that funny, but okay. We wrote what is En of f. En of f. Let me recall maybe here. En of f is something which is 1 over s f, the summation when of n, between 1 and n, we understand, of f of n. Okay? And so this is 1 of n times summation when p to the nu is at most n of f of p to the nu. So now I'm making the sum over the different prime factors, which is fine. And each time I'm saying, aha, okay, how many times do I have this? I have this a number of times which will be n over p to the nu minus n of the p to the nu plus 1. Okay, usual trick. This is fine, this is something which is correct. And now when I'm looking at the difference, I will get something where here I have no, in some way, the model, the only thing is that this n will disappear. And what I get is exactly this 1 over p nu minus 1 over p nu plus 1. So in some way, everything goes out except the big O of 1. Okay? So when I'm looking at this E of fn, En of f minus En E of z and f, what I am left with is at most something which is 1 over n times, you see, in the model it will be exactly the same thing without all that. So all this part will go out. There is here just a big O of 1 which will stay, and indeed this big O of 1 is exactly 1. And so this is the summation p nu less than n of f of p nu. Okay? Good. Now, what I want to say, I want to try to get something out of that. And what you can do is, as usual, you use, if you want to do something about this square, no, this like that. And this is at most 1 over n. And I want to, where was it? I have suppressed it. V of Zn, yes, V of Zn is here. And I said that V of Zn, if you remember, is something like that, between 1/2 and 1 times this expression. Okay? So the point is to know whether you can get something out of this which looks more or less like that. Okay? Well, we can do that. We can do that by saying this is summation p to the nu less than n of something which is f of p to the nu square divided by p to the nu. And then you will have something which will be the sum of p to the nu is at most n of 1 over p to the nu. No, of p to the nu. And this is 1/2. So what I am doing here is just to say that in this term, I consider it as being that divided by p to the nu over 2 and multiplied by p to the nu over 2. And apply Cauchy again. Fine. Now we are rather happy. because we have something which is essentially what is here, this sum of f of p to the nu divided by p to the nu, we are quite happy, except that we have to do something with this sum. Okay, the sum of p to the nu up to n. But what is this? This is at most what? Well, each element, the worst you have is something which is n. Okay, this is at most n. And then you have to know how many prime powers you have up to n. Number of prime powers up to n is essentially something like primes up to n. Okay, so it is n over log n. So we get something which is n over log n. Okay, and so with all this, you get something that will tell you that this is, you are winning something, because here you have some n times n is n squared. You have a n to 1/2, which kills this time. But you are winning something which will be a log n. So you are winning a square root of log n. And you have something which will be, let us say, big O, you may compute what it is, of the variance of z and f divided by log n. So the difference between the semi-empirical variance and the actual variance is something which is at most, then you square it if you want the variance, because you have to square here if you want to see this difference. This difference is a big O of V of Z and F divided by log n. Okay? But what you have is an upper bound of this one. We have not yet proven it, but we have an upper bound of this one, which is something like a constant times that. Okay? So you see that this term will be just about the same thing, because we are just modifying by something which is that divided by log n. And again, you can make the things explicit. It doesn't depend on f, what you have here. This is independent on f. Sorry? Yes, here I have n terms, which are something like n log n, n over log n. I mean, I have n over log x term, which are something like n. Well, you can make it more precise and not only, instead of saying all these prime factors, you can say the largest one is this, and it is at most twice, because it is geometric series with a ratio which is 1 over p, and so you get that. So you can make all this quite explicit, and so you get something which will be the number of prime that you have, and each one is at most n. So maybe it is a 2 or something like that, but this will be fine. Okay? At least when n is large enough. And so this means that you have some n square, but due to the power 1/2, this term is only one of the elements in the Cauchy business. You see, so it is to power 1/2. And this n cancel with this one, but you are still winning a tiny bit, which is enough. Okay? Good. So now we're happy to say, well, if we can prove the Turan-Kubilius business as we announced, then we're happy, because definitely it gives us also an upper bound for this in terms of the BFN, because everything on the right-hand side is in terms of this, so it's fine to have this too. Good. Okay, let us go to the proof. Okay. So now, if you look at Turan-Kubilius, maybe what we say the following, that we have V of Vn of V star n of f is at most something times V and f, V of z and f. Okay? So now you have something that all that are squares of elements. So a square of a complex number is the sum of the square of the real part plus the square of the imaginary part. So if you know how to prove that for complex function with the same constant, it's good. Okay? So it is enough to prove it for the real part and from the imaginary part, that is to say, you do it for, of course, if a function is additive, you notice that its real part is additive and its imaginary part is additive. You are just writing something like f of n is the sum of f of p to the n, okay, when p to the n divides n. And if you take the real part and the imaginary part, it's done. So you can just consider really real and imaginary function, and then when you have something which is the square of the business, modular square, it's fine. Okay. Now we are going to prove it indeed for positive function. So now we assume that f is real. So without loss of generality, we assume f real. Okay, I don't write more. I think I explained you simply that the modulus is the square, and so you don't lose anything at that level. Okay. Now we assume that you have. So okay. Okay. First, so we are going to prove something like to run Kubilius when f is positive, non-negative, and f is non-negative, but with a better constant, because when we go to f positive to f, any f, we are going to lose some factor. Let us explain that. To lose something like with the constant halves, halved. To halve something, does it exist as a verb? Halving something? To halve? No, it doesn't exist. Some say yes, some say no. Yes, with constants which are halved. You write it with a v, as in variance, but it has nothing to do with variance. Halved. Okay? Good. So the constants are halved. So this is fine again. Why is it? It is a mess to write all that, but it's not too complicated. Did I write it somewhere? I don't know, because now my notes are a complete mess. Maybe I have to go a bit further. No, it should be somewhere here. Yeah, okay. And this is enough because you have f of n minus expectation of z of fn square. I take the and then you will have to sum over n, but I don't need to sum over n and to know what it is, and this should be at most 2 times f plus of n. Should I explain what I call f plus of n? F plus of n is the maximal of f and 0, and f minus is minus the minimum of f of 0.
Yes, if you are taking f positive, then
yes, but now, okay, is a constant halves. This is enough since for f real, we have. Okay, I wanted to explain why it's not a big deal to prove it. If we know how to prove it for positive function, we are done. So you have something like that, which will be minus the expectation of z of f plus n square plus 2 times f minus n minus e of z of this z of f minus n f minus square. Okay, always the same thing, that E is linear and you are happy. So you work a bit on that and you find out that it's just the fact that a plus b square is at most, where we are now dealing with real business, a plus b square is at most 2a square plus 2b square. Okay? For those who were attending the course on automatic business when we were doing with 2 automata, they learned a much better expression, which was a plus b square is equal to a square plus b square. But this doesn't work always. Good. Okay, now let us prove it. And again, we can notice that again, want us to notice that b of f n square is equal to b of f plus n square plus bf minus n square. Because each time we are taking just the term. So either we have something which is positive or we have something which is negative. Okay? You put on one side those which are positive, you put on the other side those which are negative. There is no inequality, there is nothing about that. It's just trivial observation. Okay? So if you can prove that this semi-empirical business, that is to say the expectation of this, is at most something like constant times this one. Then you multiply by 2 and you have the variance, because we know that this is at most between 1/2 of v and v itself. So if you can get some upper bound with this, it will tell you the upper bound for v. You don't lose anything at that level, and here you simply lose a constant 2. So this is why we need to prove it for positive function with a constant which is halved. And then we are done.
So is that why you have n plus, so where n is coming from here?
Sorry?
So in that inequality you have n plus 2 epsilon. Like in the Euclidean inequality,
Yes.
you have this number n plus 2 epsilon.
Yes.
So is that because of
So of course it is halves also. Because it's just the fact that we are going to put a 2 each time. Okay? We are going to prove it with this, so it will be something with 4 plus epsilon, and then it will be something for in the other side with 4 plus epsilon, but since we are doubling it, it is 8 plus 2 epsilon. So this is why both constants are halved. 1 in epsilon also. Okay. So, wait. I think we can do everything. We can do everything today. Yeah. Yeah. In any case, if I don't do it, you'll finish it yourself. I don't want to go too much into that. So where I am now. This is done. This is done. This is done. And this is almost done, and I think it's fine. Okay. So good. We want to get an upper bound. So we assume now that f is positive, okay, non-negative. and we go to Vn star of f. So this is En of f minus E of z and f squared. Okay, no need to take absolute value, we have only positive business.
This will not work for RFN. This identity.
Sorry?
This identity. Will this also true for RFN? This identity. This one.
Possibly not, but I don't care.
You don't care.
We don't care because what we are going to do is simply, indeed what we are going to do is to compare this with BFN.
Okay, not.
Okay? And since we know how we can compare BFN, we know that this is at most one half of this one, at most one half of the other one. Okay? So what we have proved, okay, this is true, but now we don't care it any longer. Forget about this one. What we know is that this is at most BFN, and it is larger than half of it. No, the other way around. No. Yeah, it is this minus the business, so and the business is small, so it is 1 minus 1 half. Squared. Okay? And so if I prove that something which is an inequality with this one, I multiply by 2 again and I have this. You just have to count the number of 2, and at the end you will finish with an 8. Okay, we still may lose another 8. Good. Okay, so now we develop that. So this is usual mess, and it will be something that will be what I write as M2. I will tell you what is M2, but you can understand what it is from what I am going to write now. It is Z and F square, no, multiplied by En of f. So this is minus the double product, plus the square which is here, E of Z and F square. And so you understand what is M2. M2 is simply what you get only with the F square. Okay? So you expand the square and then you sum, and so it will be the mean value of n square. So n up to n of f of n square. Okay? Again, this is what is in the real life. So what is that? This is 1 over n, summation n up to capital N, and then you have something which will be summation when p nu divides n, q mu divides n of f p nu f q mu. I'm just squaring the function, you know. The function is times p nu divides n of f p nu, and when I square it, I have something like that. Good. Now, this is equal to something which is, first of all, you have the terms which are squared. So it is p nu at most n of f p nu square times 1 over n summation n up to n and p nu divides n divides exactly n of 1. So this is the term which is squared, the diagonal. Okay? And then you have this p is equal to q, and then you have p different from q. And then you have something, and again it is always the same thing. If you have p different from q, and if you know that p to the nu divides n and q to the nu divides n, then it means that the product divides n. So now you have something which is p nu q mu at most n, because otherwise they are larger and we assume that the function is 0. We're just interested in the value f of n which with n up to capital N. We said otherwise it is 0 if it is larger. So we may assume that this product is less than n, and what else? And p different from q, of course, is the non-diagonal term. And of course you will have p of a nu f of q to the nu, and how many times do you get that? You get that 1 over n times, this is the 1 over n, times the number of n for which you have exactly this, which is that. So this is the number of n up to capital N for which p to the nu divides n, and q to the nu divides n. Okay, I don't want to use something like p to the, that the product divides exactly n. Okay? Of 1. Now, what can we say about all these sums? This one is okay. We need to get something which is an upper bound for that.
So, how do we get f of p power mu whole square? In the diagonal, p will be equal to q, but the mu need not be equal to mu.
Ah.
We'll probably still keep f of p power mu, f of p power mu.
No, wait a minute. If you have, if p is equal to q, then when you say that, it means that that p nu divides exactly n. Okay? It forces nu to be equal to mu. Yep. Okay. So now we are at this point. So what is this? This point is something which is n over p nu. This sum. I just take upper bound with the one which are divisible by p nu. Maybe there are a bit more, but I don't care much. And so I have something which is f of p nu square divided by p nu. So if I have f of p nu square divided by p nu, I am very happy because I am well on this side. So I am here, at least even for the 1. Yes, but 1 minus 1 over p, maybe you multiply by 2 and you're happy. Okay, you put a constant and you are done. Good. So this one, you are on the good side. Well, maybe the constant you get is not exactly the right one, but in any case, you understand that at least getting a constant, you are on the good side with this one. Okay? So now we have to deal with this. Okay, to deal with this, we have to understand what is this number. This number is here. Well, you are asking the number of elements up to n, which are exactly divisible by p nu and q mu, and then you get something. By the way, here, yeah, possibly I could have said here that if I am asking f of p nu to divide exactly n, better to put immediately here the 1 minus 1 over p. Yeah. Okay, this is what you meant. Better to put it here, and you have it, yeah, immediately. There's no point to do something stupid. Okay, same thing here. Then you ask that n is divisible by both of them, and so the number of them is something like, this number is at most something like what, n over p to the nu, q to the mu, times 1 minus 1 over p times 1 minus 1 over q, and maybe you have a few elements which are left, you have big O of 1, and you can say, what is this big O of 1, because you want everything to be explicit, but you can say what it is. I think plus 2 is okay. good. Okay, so where are we now? M2 is at most, so you get something from here which will tell you that it is, no, it was written like that. M2 is at most what? 2bf of n square plus, what do I have here? You have to understand, because I let this E, I should write to you, you remember what it is, but I don't. What is this expectation? What is this expectation? Is the summation of p to the nu is at most n of f of p to the nu divided by p to the nu 1 minus 1 over p. Okay? So you have something which is okay, because you have something which is the n which disappears with this one, and you have something which is p, you divide by p to the nu, and you divide by q to the nu, and you have just the factor which are fine, and this will be something like the square of this. Maybe you have to plug in some diagonal term, you don't care much about them. So again, you will get something like that this is plus 2e of znf square. You just you square it and you get that. And you have this term, which is the term which is a bit bad, but you don't care. This is plus 2 over n, something which will be the sum when p, nu, q, mu are less than n, and p is different from q, and then you have f of p nu, f of q mu. So it starts to look rather fine. What about the last term? Again, last term, you want to do it in force, to do something where you recover this p nu, okay? And in order to recover the p nu, you just use Cauchy again, okay? Always the same old trick. And so you use Cauchy, and by Cauchy you will get the following, that the last term, for the last term you use Cauchy, can we do something in number theory or even in mathematics if there is no Cauchy? Possibly not. Okay, so you have p nu, q mu, p different from q, of f p nu, f of q mu divided by p nu over 2, q nu over mu over 2, and then you have something which is this. So for the time being, I've done nothing. Q to the mu over 2. And now I use Cauchy, and I said this is at most what? And I get something where I will recover the product. I will recover this BFN 2 times BF of n square times something which will be the square root. You see, when you have the square of those business, you have something which is essentially this term. Maybe you don't have this 1 minus 1 over p, but 1 minus 1 over p is at most 2, at most 1/2. So to get it, instead of having 1/2, you multiply by 2 and you are sure that you are done. So this will be what you get from those terms, is what you get here. The 2 is what you get from the 1 minus 1 over p. And then you have something which is the summation. Again, it is just a summation of p nu, q mu, and p different from q of something which is p nu, q mu. Just the term which is here. When you sum this term and you square it, so you don't have this, but Cauchy tells you you square at the end and you have that. I think we are more or less done now. Okay. So what is the problem here? So this is something which just depends. This is the factor, you see. You have a factor in terms of in front of the b square, which just depends on p and q. This is part of the epsilon n. Okay, so this enters into the epsilon n. I told you what was exactly epsilon n. You recognize that this is part of the epsilon n. So here, for this term you are happy, and for this term you are happy. So now there is something which will be bad still, is that you have this term. Okay? You have this term, but again, this is not that bad. Because this term, yeah, it was the right decision to do that. This term is E of Z of NF square. This is this term. Okay? We're happy with this one. We're rather happy. We knew that it would be an error term, you remember? This is something essentially in n, and this is something which is an error term. Simply this error term, you're able to say it is an error term, but an error term with a factor which has nothing to do with f. This is the good guy in the upper bound, and this is a small term which does not depend on f. This is the trick here. Not only to say this is an error term, because it could have been an error term which depends on f, but we'll say, no, it is an error term which is what we like times a small term which does not depend on f. This is what Cauchy does in some way, is to separate the variables. Okay? So what is this? So this is at most the summation when p nu is at most n of f of p nu square divided by p nu times 1 minus 1 over p, and then you have a summation. Again, what we did is to use Cauchy again and again, and then you get something which is p nu is less than n of 1 minus 1 over p divided by p nu. Okay? So this is fine because we have recovered from the expectation of Zn. I don't know if I still have it somewhere, but you have it, and you understand that just by Cauchy we do this. So we're happy because we get back something which is our b nf square, and then you have something which is just something which doesn't depend on nothing. So this is at most what? This is at most so this is at most b nf square times the summation, and then you just put 1 over p when p is up to n. You sum the geometric series. You see this is just convergent, and it gives you 1 over p because you start with a 1. If you start with a 0, then you have something which is the total sum, but you start with a 1, and this is why you gain this factor 1 over p. Okay? And again, then you know what it is. This is something which will be something that log n, which is what you. Why do we like it? I don't know. Why do we like it? This log n. This is not good to have something like that.
It was coming in the epsilon n.
Epsilon it should be part of epsilon.
No. This sum is a log. It is more than a constant time the business. It's not good. There's something I missed there.
No, actually epsilon n is not.
When it is a term, right? So
that term, summation q u, all these things are coming with epsilon.
Yeah, this one comes into the epsilon.
And this one
plus one more term was there.
Yeah, this is of the same order. Wait a minute, but then I don't understand because I have very large terms here. You see the point here is that here I have a 1 over n. This is why I'm happy, because I have a 1 over n times that, and this is small. But this one, I don't have a 1 over n, or I did something wrong. Maybe I wrote it too quickly. I have to write what it is, because in this expectation there is a 1 over n somewhere, and I didn't write it. Sorry? Yes, no, this is the point, that there is a log n. So I have to recall what was this expectation of Zn. I possibly didn't write it correctly, this E of Zn, where it is now. This is the problem, that I mixed up everything. Yes?
This one is getting cancelled in your expression. And just the second line, you have expectation squared Znf, which is, okay, so you get twice. Okay, no, it's fine.
No, it's fine. This exists. No, I just have to understand what it is. Possibly I didn't write the E of n correctly. E of Zn. Where is my E of Zn? No, E of Zfn. E of Zfn is the summation over Pn less than n of f of p nu divided by p nu times 1 minus 1 over p. So the 1 minus 1 over p, this is not the thing which is important, but
That is summation 1 by summation p also should be there. Because Zn is summation of the geometry random function Zp, and then you are substituting on Zp. The expectation is sum, and then there is another sum.
so now what I am doing here is to say I'm writing that this, I keep it completely. I mean, this has no importance. As regard the constant, I don't care about the 1 minus 1 over p. This is not important, because it is essentially, it is always between 1/2 and 1. So it is absolute constant. I want to understand where I get something which is really interesting. So 1 minus 1 over p. Okay, I put it 1/2 and 1/2, so it is at both sides. Then I square that, and I have p to the nu over 2, and I square it. And since it is square, it is this one with a square times this sum.
So your Zn is sum of Zp. Is sum of Zp. So
Yes.
the expected value is the sum of the expected value of
Yes.
Zp. And then this is the full sum.
Yes.
So there should be another sum, no?
Sorry? No, this is fine. This is the expectation, and so it is the expectation square. And when you take the expectation square, you are breaking it, saying that you take this to 1/2, you take this to 1/2, and then you make also, you multiply by 1 over p to the nu over 2, and 1 minus 1 over p square, 1/2. I missed something here. Sorry?
In the second line, if you prove that the third positive term is smaller than the second negative term, then you are through.
Yes.
You can forget both of them.
Yeah, because the first and the second we did already and we are happy with.
Yeah.
Good?
The third term is less than the second term, that's all you have to prove.
Yes, this is fine. And
Which means you have to prove E of ZNF is less than 2 times E of ENF. And that is clear.
I don't know what is clear now any longer.
No, we are not even squaring it. Just only one E, no? It's linear.
Here?
Yeah, I'm saying the third term is less than the second term. And therefore I can forget, and upper bound I can forget it.
No, but in the first term you have another one sitting there.
What?
M2 is, M2 is
See, third term is coming out from the first term.
Yeah, I think I understand what you mean, but I don't understand where I am doing something wrong here. Ah, you mean I shouldn't use Cauchy there?
No,
No, you use it, what he said is.
it's just to prove that E of ZNF is less than En of F.
The third term is less than.
Ah, yes, okay.
Sorry.
Yes, E of Z and F is less than that,
And that's all you
Then
have.
you.
and then I have at most.
No, one more E of ZNF whole square coming from the M2.
No, then I don't have it. Then I have just M2 to take care of.
No, that two if you forget, if you show the third term is less than the second, without the two, then you are okay. Because you don't.
Yes. Yeah, if the third is less than the second, it's fine. You mean using the fact that this is negative?
Yes,
Yes,
there is a minus 2 there.
Yeah, there is a -2.
that's why you
So,
have two of them.
so if I can prove that E of Z and F is less than E of N of F, I am done.
And that's clear.
And this is fine. And this is why we use positive functions, by the way. Yeah. Yeah, using Cauchy all the time is not that great because then we're losing the fact why we are taking positive functions.
You lose your log.
Yeah. And so now we don't have the log because we're using the positivity. And so this is fine because we're really subtracting something, which is better than that. Okay. So, well, we are done with that. We'll use that tomorrow morning to get some normal order, to say how it can be used for getting normal order. But in the afternoon, we are going to talk about, we have not yet gone into that, the distribution function of arithmetic functions, real arithmetic functions. Also convergence of measures, there are a few things to say. And starting the additive business, where we will really see the probability. Okay? And then we'll end on Friday.